Hello, my name is Nishka Shah, and today I'll be delving into the Hodgkin-Huxley model. The brain is a complicated yet fascinating organ that controls our thoughts, emotions, and our processes in our body. But how does it do all of this? The brain, along with 150 billion neurons, control and receive signals that perform specific functions. The pioneers of computational neuroscience, Hodgkin and Huxley, were the first to create a mathematical illustration of how neurons communicate using chemical and electrical signals. In this video, I'll derive the four equations surrounding the Hodgkin and Huxley model, the voltage equation, and the equations for the gate variables of sodium, potassium, and leak. So let's get into it. So the Hodgkin and Huxley model surrounds neurons and their membranes. An example of this, a simple example of this, could be represented using an RC circuit shown here. So an RC circuit contains a resistor and a capacitor, and current is injected into it, which will flow through the different components. There's also a potential difference of U. To find the total current in the circuit, we can calculate that by adding the current of the capacitor plus the current of the resistor. First, let's find the current of the capacitor, which can be found using the equation capacity equals charge divided by voltage, which is C equals to Q by U. Now let's multiply C with U to get charge on its own. And to find current from this equation, we can differentiate the voltage and the charge to find the current, as charge over time is current. So the IC would equal to C times du by dt. This can be input into this equation once we have both the answers to IC and IR. Now let's find out how to calculate IR. IR can be calculated using the formula that's derived from the Ohm's law, stating that V equals IR. So to find the current, we would do voltage divided by R. And to find the voltage of this resistor, we would need to subtract the voltage of this battery from the total voltage and let the voltage of the battery be U rest. So U minus U rest times 1 by R equals current of resistor. Yes. And now both of these can be input back into the total current formula. So to calculate the total current, we can do C times du by dt plus 1 by R U minus U rest. Let's subtract this and bring it to the other side. So C times du by dt equals to IT, so the total current, plus 1 by R times U minus U rest. Now, to simplify this formula, we would need to multiply both sides by R. So RC times du by dt equals to, this would would be a subtract sign as it was taken to the other side. So since we multiplied this with r, the r's would cancel out, bringing this to minus u rest plus r times it. And to notice the units for all the parts of this equation, this would be volts, as volts divided by time would be volts, and volts minus another voltage would still be volts, and R times I, according to the Ohm's law, is also voltage. So for all three of these, the units would be volts. So for IC, this would convert into tau as that is the standard constant, that is the constant of this RC circuit. So this can be written as tau times du by dt equals to minus u rest plus r times it. And this can be simplified further as the u minus u rest is basically voltage, so it can be replaced by v. So tau times dv by dt equals to minus v plus r times it, and this would be the final voltage equation for the Hodgkin and Huxley model. Now let's move on to the Nernst equation. So let's move on to the Nernst equation. This equation can be explained with the help of a diagram of the cell membrane of a neuron. So the cell membrane can have open channels and closed channels, and the inside of it could have a higher concentration of potassium ions compared to the outside, which has a higher concentration of sodium ions. These can be differentiated using dots and crosses. And the ion channels, which are these, pump electrons in and out of the cells, which causes a change in concentration, eventually causing a change in potential difference. This causes energy to be generated from the particles, which can be represented by the equation energy equals to charge times PD, potential difference. Or we can symbolize that with U. The dependence on the energy is exponential, and this dependence is called the Boltzmann distribution. And this can be represented using the formula n is proportional to e to the power of negative e divided by k times t, where n is the concentration, E is the energy, K is the Boltzmann constant, and T is the temperature. And we can compare the density or the concentration of the inside and the outside. So let's say the inside is N1 and the outside is N2. So to compare them, we would do, let me divide n1 by n2 equals to e to the power of negative e1 divided by kt divided by negative e2 divided by kt. Now, the ratio of the exponentials can be written as the difference of e1 minus e2. So, this can be represented as e to the power of negative 1 kt times e1 minus e2. And this equation that we had just talked about, the energy equals charge times u, can be substituted in this formula where it's e, so e to the power of negative 1 by kt times q u1 minus q u2, and this can be further simplified into e to the power of negative q kt times u1 minus u2. And we can now apply a logarithm to solve the exponential equation. So that would be ln of n1 by n2 equals to minus q by kt times u1 minus u2. And we are interested in the difference in the potential, so this can be represented as delta U. And N1 is the concentration inside of the cell, whereas N2 is the concentration outside of the cell. So the ratio between the ratio of the concentrations and the ratio of the volume, the voltage difference inside and outside the cell is the ratio described by the equation called the Nernst equation. Now, I'm going to need another page. However, this equation can be carried out further. So the delta U equals to delta U basically equals to U1 minus U2, which also equals to minus KT as we cross multiply in the previous scenario. So we will get KT as the numerator and minus Q as the denominator. So going back, KT divided by Q ln logarithm of n1 by n2. The inside and the outside concentrations. So to summarize, the ion pumps cause a concentration difference, which causes a voltage difference, and this is described by the Nernst equation. The voltage difference, this is important, the voltage difference is also called the reversal potential. This will be used in our next equation for the three equations for the Hodgkin-Huxley gates. Thank you. Now we're going to discuss the Hodgkin-Huxley equations. So Hodgkin and Huxley inserted current into the axon of a squid, which works as a circuit, as I have displayed here, and they found the two dominant types of ions found were potassium and sodium, and there was a leak type of ion, which was a summary of all the other ion channels. And since these are resistors, these can be described as RK and RNA and RL. And this is the capacitor, and current was inserted and was distributed along the circuit. So to find the total amount of current, we need to use the formula IT equals IC plus IK plus INA plus IL. And we have already discussed how to find IC. I have derived it already, that capacity equals charge divided by voltage, and C times U equals to charge. If we find the derivatives of voltage and charge, we will get C times du by dt, which equals to dq by dt, which equals to the current, as charge over time equals current. So it can be written that IT equals to C times du. Actually, we can bring C times du by dt on one side and then try to bring everything else on the other side to solve this equation. So minus IK minus INA minus IL plus IT. And now we need to bring in Ohm's law, as the rest of these formulas will follow Ohm's law. So U equals to I times R, and to find R, we need to do U divided by R equals to I. Now, to find the voltage, the total voltage is the sum of all voltages across the cell. It has two components, the batteries, which I have circled now, and the channels, which are the sodium, potassium, and leak, which is the reversal potential calculated from the Nernst equation, which I had mentioned earlier, for the three channels. Because the ion pumps change the concentration, they also change the voltage and causes it to act like a battery. Hence, the voltage of potassium, sodium, and leak would be described as the following: minus 1 by R, as V divided by R is V times 1 by R, times total voltage minus the voltage from the battery for each component. So RK minus 1 by RNA times U minus ENA plus 1 by RL times U minus EL times plus IT. And this is sometimes called the first Hodgkin-Huxley's equation. However, the difficulty was that the resistors K and NA are not constants, they're variables. So when a channel is open, the ions can pass through it, even if the channel is open, it has some finite width, which means that it still has some resistance. So one of the resistance, so moving on, one type of resistance is called conductance, which is just denoted as G and is the reciprocal of resistance. So it would G equals 1 by R. If we input G into this, we will get GK times, I will leave a gap here, times U minus EK minus GNA U minus ENA, I will have to go to the next line, minus GL for the leak times U minus EL plus IT. So I have left some gaps here, as you can see, because the channel may not always be open. The channel may also be closed. The conductance in that case is very different. Hodgkin and Huxley described a gating variable N, which describes the state of the gate. If N is 0, then ions cannot flow. If N is 1, then the ions can flow. So they found the description for these dynamics of these gating variables N, M, and H. For each of them, they write down an equation of the form dx by dt equals to minus x0 divided by tau. The negative sign here means that x is likely to tend to minus x, positive x0 exponentially, as x0 is more stable, especially with the time constant tau as its base. So these gaps I will fill now. For potassium, the gating variable is N, and for sodium it has 2. It has M and H. Let me move on to a new page. So, as I mentioned before, for every x value, it would be d over dt equals minus x0 divided by t, divided by ti. And they have created 3 equations for N, M, and H. So this would cause, if it was the equation for N, the equation would look like N dt equals minus N0 divided by ti, and tau. And one thing that I forgot to mention is that the powers for this equation this linear equation described the behaviors almost accurately, but some of the delayed activations were not correctly described. And therefore, Hodgkin and Huxley proposed not to put the power 4 and M to the power of 3. So M was to the power of 3 and N was to the power of 4. And moving back to these equations, for M, it was d by dt and M equals to minus M minus m0 divided by tau. For h, it would be d by dt times h equals to minus h minus h0, and they were all multiplied by the voltage. Tau times voltage. So let me go back to this equation and change the color. So the first equation, which represents the conservation of current, and the equation on the right side represents the sodium current. Which means that the current that can pass through the sodium channels that allow sodium ions to pass through when open. Second is the potassium current, and third is the leak current. So the whole thing is driven by a stimulus, which is IT. This is the stimulus. And for each gating variable, like I mentioned, it was dt, d by dt, and the variable minus the variable times 0. And there you have it. These are the 3 equations for the gating variables, and this is the main Hodgkin-Huxley equation. And to this day, the Hodgkin-Huxley model, comprising of the 4 equations, are used in modern day areas of neuroscientific research. Thank you for watching my video.